press the button. Okay, I guess it's being recorded. Yes, it is. No questions? So, it actually works. Today, it actually works. Very good. The first homework set is up on KLMS, so you can go check, play with it, enjoy, struggle, whatever. Okay? I don't think I've made very difficult problems, but nevertheless, you can go and check. So I will start today's lecture by first quickly reviewing what I talked about towards the end of the last lecture, meaning the general representation of the Poincaré group acting on the quantum state, not a quantum field, but acting on the quantum state. Okay? Because I was somewhat rushing through that, and also there's a few points that I want to make sure to deliver to you, which are important, and hopefully you can actually look at the equations and then can read the meaning of those expressions. Okay, so I want to first go through somewhat quickly, but nevertheless, I want to make sure some of the important points are delivered. And then today we will start our actual discussion. You will see for the first time the appearance of quantum field. But instead of me just writing down the expression for the quantum field, I will derive it to you. Okay, why in a particular form of today's scalar field? That scalar quantum field is the one that you need to ensure Poincaré invariance, unitary, and causality. Okay, so that will be hopefully the content of the lecture. And then we will start developing the machinery for the quantum field. But first, let's talk about briefly Poincaré group and how that's represented on the quantum state. So last time I defined my quantum state with the momentum P to be P and then some whatever labeling that I reserved for sigma. And then I defined that to be a starting from what I call the standard momentum. Standard for momentum, which I will spend some time talking about it, but I'm gonna boost it using Lorentz boost. So last time probably I used LP. So the definition of this LP is that given any momentum P mu, for momentum P mu, I will get it starting from standard momentum by boosting it. Okay, so this is boost. So maybe I just use a simplified notation just to call L sub P. Okay, it's too much parentheses and so on. And then you understand that L sub P just means that you take a standard momentum to your physical momentum P. Okay? So even before I jump in, let me already talk about it. So for time-like control vector, where whose square, Lorentz square, is positive, so real physical one, okay? You can always boost. You will see more details of that. You can always pick a boost such that arbitrary time-like form momentum can always be boosted back to K, which basically has a mass of 0, 0, 0. Okay? And so I spent some time to talk about that today, but you may already remember my discussion that for these time-like vectors, you have two hyperbola or hyperboloid in 3D sense, right? Like that, right there. We talked about it. When we talked about proper orthogonal component. So what I'm saying is that for given any form momentum, you can always boost back to this point, where you don't have any spatial component, you only have a temporal component. In terms of the energy of mass, obviously if you boost it back, there is no free momentum. The only energy contribution to the energy is just the mass, that's all. Okay, so remember that. And then for light-like or no-light case, where that corresponds to massless particle, then again you can boost your such vector to a standard vector basically it has a E00E. Basically, you have a massless particle traveling along the z direction, and then for massless particle, the size of the momentum should match to the energy cell, right? So that's the choice we can make. Good. So then we are interested in how given Lorentz transformation act on the physical state. That was the question. Okay? And then if you recall, the first exercise I did, I just acted with the momentum generator. I just put head temporarily to make sure this is an operator. And then I did this exercise to show that, you know, this should be proportional to lambda p state. And then some sigma index, right? Which physically makes sense because you had a momentum p, and then you just did the rotation or boost, so you expected that. And we're gonna make that statement sharper, which already I sort of did it. So let's actually walk through the exercise that I already did it. So I start out with this. Oh, I forgot one very important thing. Not very important thing. One thing. I forgot one thing. Some normalization. Okay. Some normalization. So I can first write this as a N of P. And then, so causal P, so I'm using the simplified notation. So far, so good. So the way you read off is that you take the K, boost to the P, and then rotate to the lambda P, right? So that motivates me to do the following. So N of P. So I'm gonna first take that, U lambda LP, acting on K. And then I'm going to boost the backward. How? Lambda inverse lambda p. So I'm just going to bring this guy back to k. So that's what this boost does, right? So therefore I'm just going to insert identity by having a u and u inverse. Good. So then one recognizes that this set basically takes the k back to k, as you saw here. So that is the definition of what is known as a little group, but this is a operator version. Okay? So by definition, this little group takes a certain momentum, and then it transforms, but it brings it back to itself. So it doesn't change it. So this set of such transformation is a form of subgroup. It's a form of subgroup. In particular, it's called a little group for a choice of k. Okay? So little group for k. Okay? Now, since we already have this, let's quickly just talk about what might be the little group for massive time-like for vector, so k. So if I choose k like this, okay? And we can ask what set of transformation leaves this k invariant? Well, at least one thing is totally clear. If you take any transformation x on this 3 spatial part, obviously it doesn't change the k. Okay? And turns out that little group for this one is actually either SO3, but more precisely, actually SU2. So if you ever heard of that, this is like a complexified version of this, or double cover of that, or universal cover of that, whatever. For massless case, one obvious trial is that if you take a rotation that rotates these two, seems like it doesn't change the k. So that is a rotation acting on this two-dimensional space, SO2, which is basically the same as U1 rotation. Basically, you have a stick pointing along the third direction. Obviously, if you do the U1 rotation perpendicular to that point, which leaves that stick invariant. It turns out that slightly more precise analysis show that actual little group is ISO2, otherwise known as a two-dimensional Euclidean group. Two-dimensional Euclidean group basically means you imagine that there's a two-dimensional plane. And there's a wrong rotation one can do, but you can also do the translation along that plane. Okay, so that's that. But there's a sort of physics discussion one can think about, but eventually it is sufficient to think about this point. Okay? Now, having said that, are we, as a whole community, completely settled on this versus that? The answer is no. Okay, still there is activity, real-time research going on, see if this can actually be the correct structure of the universe. And what will be the observable one has to see, and so on and so forth. This is still going on, but for the purpose of this lecture, it is sufficient to think about this. Now, we will quickly see, so let me continue on this side, but we will come back to this side again pretty soon. Anyway, so what we have done is that take the Lorentz transformation acting on physical state, and then we arrived at this point. So let's understand what that means. Let's first understand this part of the story. Okay? So what that tells me is that if I have a little group acting on a K state, that by definition doesn't change K. So the only thing that this can possibly change is this whatever the sigma index. Okay? So this will do sort of basically leaves the K invariant, but it can rotate the sigma index. So let me just use this, if you wish, this is nothing but a representation matrix of this operator. Okay? There's a rotation. No, so what is that? For massive particle state, okay, this rotation for SO3 or SU2 is actually not this. This is nothing but spin index. So we can have a spin 0 state. Yes.
Is D the Wigner-D matrix?
That's correct. This is exactly Wigner-D matrix. Okay. So then, you can have a scalar particle. Scalar means that there's no non-trivial structures. Basically, everything is exactly point-like, no actual spin. In that case, so for instance, for scalar, and we now talk about Lorentz scalar, Wigner matrix basically delta, meaning there's nothing to rotate. Okay? You can have a fermion, which may have a spin, in this case, spin half. Then you can have up and down. So there's a two state getting rotated by this rotation. Okay? You can have a vector. For instance, you can have a spin 1. Here you can have a plus minus 1 index for sigma. And sigma you can have a plus minus 1 0. So there's a 3 state gets rotated and so on and so forth. Okay? So that's what this is telling you. What about the massless particle? So for massless particle, we just talked about the fact that the little group, you can think of it as basically U1. And for U1, it's abelian growth, and you can always represent this Wigner matrix, or not matrix, Wigner thing, as basically like that, so as a certain U1 phase. Okay? And it turns out, therefore, the correct quantum number associated with quantum number is A, which is what's known as the helicity of the particle. Now, something great happened, unless, in case you spotted it already, something amazing happened here. So let me summarize by actually now finishing the game. So let me now continue from there. So I wanted to study this. And eventually what happened was that, so this part literally collapsed to that part. And then I can now take boost, which takes the k to lambda p rather than p, right? But by definition, if I act this guy on k, at this level, I get a physical state with the momentum lambda p, right? But the only thing that I need to worry about is that I define the physical state with certain normalization. So I have to multiply and divide by. That's all I need to care about. So with that small detail, done. So let's look at this equation and understand the power and the meaning of this. I wanted to study that. I knew sort of by physics intuition that if I take the p and then rotate by lambda, I should get some linear combination lambda p, which I'm getting. Now this construction tells me the exact which linear combination should I have to get, right? And therefore, what is a representation space actually? And you might say, oh, lambda is a nasty object. It has a nice rotation, but it also has a boost. The boost is a non-compact transformation. That sounds like a pretty tough thing to deal with, right? It's non-compact. However, this construction basically collapses the question of this representation story down to understanding what is the representation of this little group. So for any state, you can always boost back to standard moment k, and then you just need to worry about a set of a transformation acting on the k invariantly, known as little group. And little groups are always compact. So the entire representation story collapses down to understanding based on little group transformation. This is called induced representation. Okay? For any arbitrary momenta, you might say, oh, that's very tough because there's boost, non-compact, oh god. But you can always collapse to compact subgroup, little group, and that thing can be understood nicely, right, in terms of method representation and compact. Okay, so it's called induced representation. That equation basically captures that story. Okay, so anyway, I just wanted to flash out some of the points that I didn't have time. Okay, so that's that, and we're gonna move on to constructing one of it. But if you have any questions, feel free.
주어진 람다에 대해서 W를 추측해낼 수 있는 분명한 단계의 공식이.
So in a sense, this is not lambda dependent. This is actually p dependent, right? So for any actually the lambda W is not very much p dependent. The only dependence is that whether p is massive, massless. That's all, right? For massive, massless, there's a universal W, which is either SU2 or U1, period. Right? So in that sense, that is pretty much universal. Any other questions? Okay, so today let's see. I don't know what that means, chapter 3 means. Have I ever written down chapter or something before? Then screw that. I'm not going to do that. What did I say? 1 and 2? Something? Did I say anything? Any numbering scheme?
2 was many particle physics.
Right. What did I say? Did I say chapter or section or just 2?
Just 2.
Okay, cool. So just 3 then. So let's see how we can construct a causal scalar field. So to this end, so let me say the word. You may remember the first exercise we did, which was to say that I want to describe a relativistic particle with mass m. And then we write down our down trial Hamiltonian, which is square root of p squared plus m squared. And then we ask, oh, okay, so I'm going to start with a localized state as the initial state. So I want to start from an initial state where this is completely localized. And then we time evolve using our down trial Hamiltonian. And then I ask, okay, if I measure that at a later time in such a way that this P of nx are spatially separated from the initial point, right? What is the probability density of that? And the exercise we showed was, okay, so that was not 0, so it looks like there's a causality violation. That's the exercise we did. Now, in this case, we're talking about what's known as the Schrodinger picture. Probably you have learned that. So here we're talking about a state, right? And then we evolve the state, and then we ask the question, such as that. Now, we're going to start talking about things in a Heisenberg picture instead. So, so as a first thing, let me quickly remind you or tell you. Because I want to construct the causal scalar field operator, right? So I want to talk about the operator. So what is the difference between Schrodinger versus Heisenberg picture? So here, okay, states evolve in time, but operators are independent of time. Okay? On the other hand, as you will see some details, here states are time independent. Here, operators evolve in time. So let's just remind quickly what those were, and then we will proceed. And then I will basically spend a few minutes to ask how to formulate the question. So we should be able to formulate the question properly, precisely enough and detailed enough that the task becomes clear, right? That's the crucial part. Task is algebra, as you will see. The really crucial part is, this gigantic big title. What is the precise action item I have to identify, right? Then we can go on and they can do algebra. So that's the task. So before that, so therefore let me just very quickly remind you of those pictures. Professor? Yes.
Before raising that,
What if I erase very quickly?
I have a question.
Yes.
Is there any restriction on H? So I know that the
Yes.
KAIST is plus minus 1 part.
That's right. Good.
What?
Where did that come from?
Yeah.
Okay, good. So if you just waited 3 seconds, you lost that chance. So that turns out that the Lorentz group, as we talked about, right, is actually, okay, let me just say very quickly. We talked about like the proper orthogonal sector, and then there's two discrete transformations to go from one sector to all other 4 sectors, right? We talked about that. However, it turns out that, really correct thing to think about is the spin 3,1, which is a double curve of that thing. Anyway, because of that, turns out that for this Messer's case, it is not 2 pi rotation that bring you from original point to starting from one state to each state, but it should be actually 4 pi rotation that bring you to itself. So that means that if you demand, so this is a quantized eigenvalue, so if you demand this, you learn that H should be 0, half, 1, those are felicities.
Yeah.
Did I answer your question?
But the helicity is in particular chosen to be plus minus 1 part.
Well, I'm telling you that it can be any of this.
So you mean the arbitrary hard functors?
Yeah. So for instance, I have a scalar, massless scalar. I can have a massless fermion, left helicity fermion, right helicity fermion. I can have a photon, I can have a polarization +1, -1, and then +2. I can have a graviton, this is gravitational wave related phenomena. We can have +2, -2, keeps going. But although above that, there's a theorem that it's hard to have a massive theorem. Why are we there? Okay.
But we have not seen any spin 3 hard particles.
So, very good. Okay, yes. Why didn't I write it down?
So we encounter plus minus 1 or plus minus 1 part.
Yes, we have this, we have that, and probably we can say that we have seen this.
Yeah.
We haven't seen this, and seeing this is a gigantic discovery known as a supersymmetry. There are gigantic amount of effort happening in LHC. Oh, we are not looking for massless case, by the way. For technical and phenomenological reason, we are looking for massive spin, not the helicity. We have case. We haven't seen that yet, as you said. Okay, that signals a supersymmetry. We haven't seen it. We would like to see it, but we haven't yet.
그리고 U1의 프로젝티브 레프레젠테이션은 반드시 그 2디멘션은 이유가 있어요.
So you're
선택할 수는 없어요. 플러스 2분의 1이랑 마이너스 2분의 1이랑.
You're asking, are you asking this question or you're asking general mathematical question?
그러니까 지금 플러스 2분의 1을 추주하면은 마이너스 2분의 1을 추주해야 되는데 해야 된다고 말하시는 것 같은데요.
Sorry, can you say that again?
플러스 2분의 1을 선택했으면 마이너스 2분의 1도 그 페어로 존재해야 되는 건데.
No, I haven't said that. I just said that these are possible values.
예, 근데 근데 실제로는 플러스 마이너스, 그러니까 그 플러스 마이너스가 페어링을 이뤄서 그 스테이트를 구성을 하잖아요.
But they are not perfect pairing though. It's related to whether your physics respect the parity or not. So there are certain physics that respect perfectly parity, which are related to like, so parity flips this to that, and vice versa. Okay? We will spend some time. So your physics completely respect the parity, then you will see for every observable, you will always pairing effect. But standard model particle physics, by the way, does not respect the parity completely. So, for instance, left-handed electron versus right-handed electron, this thing couples the photon Z and W, that couples only photon. Sorry, more precisely hypercharged. Okay? So it doesn't actually completely parallel. There's an actual difference. Whenever that happens, we say the theory is chiral.
그러니까 theory dependent.
Yes, it is a theory dependent. Okay. We want to have a good formulation of the question. Let's do it. Another question. You have last chance. Now go. I refuse to address. Okay. So what are those differences? So let's first talk about Schrodinger the picture very quickly, and then Heisenberg. Right. So here we imagine there is a quantum state which is a time dependent. So let me just actually put S to denote that it is in the Schrodinger picture. Okay? And you know how that evolves according to Schrodinger equation. And therefore, in this case, the question is to find the entire dynamics is captured in this time evolution operator, all right? Unitary time evolution operator, such that T can be constructed with some properties, which I'm not actually saying in detail. Okay, it should be unitary, blah, blah, there are properties which we will develop that later. Anyway, so here in this picture, state evolves according to this. However, operator, so operator, if you have Schrodinger picture, this is time independent. So this is a scheme. This is a representation of the physics we decide to take. Okay? This is not the only possible way to describe physics, but we can choose to take this physics, to do this. What about the Heisenberg picture? Hi. So here, we want to consider that state in Heisenberg picture. It doesn't change over time, but operator does. Okay? But how does the operator evolve according to, how does the operator evolve in time in this picture? Well, you can find it by imagining that the physics has to be the same in either picture, right? This is a choice of description, not the physics system. So you can for instance say that, here is the Schrodinger picture, Schrodinger picture. Let me first write everything in Schrodinger picture. That has to be the same as in Heisenberg picture, right? Physics has to be the same. So if you compute the expectation values, which are observable, it has to be the same. Now I can choose, this doesn't evolve, as we said, this is Schrodinger picture, and then I can choose, I match two descriptions at 0 point, right, together, Heisenberg versus Schrodinger. Here, you can choose that this doesn't evolve because that's the property of Heisenberg picture, and then you can choose once again that matches to Schrodinger picture state when at time equal to 0, right? That's the matching point of the two description. And then once you have these two, and you can read off basically. So this is say T, right? So if you plug in, you can immediately get that the operator in the Heisenberg picture has to evolve according to U dagger. Right? So that's how things work. And then you can plug that expression here, basically, And you can actually derive that that thing up to plus minus I. That may not be precise. So here, the time evolution equation is known as Schrodinger equation in Schrodinger picture. And analogous thing that controls time evolution of an operator in this picture is known as Heisenberg equation for good reason. Okay? So those are the two things. Now let's go back to this question. So previously, the physics question we were asking was if I prepare a state, let it propagate, and then let me measure whether I can see the particle at a point which are space-like separated. Whenever I see that, I say there is a causality violation, which is bad. What will be the analogous formulation in Heisenberg picture? Right? I prepare a state, okay? No time evolution of the state. And then I want to do a measurement, which are space-like separated from whatever the state I prepared. And then I see whether my measurement tells me something about the original state, right? That should be the formulation. So let's be more precise. So let's consider the following. So if this is t and x. So suppose I consider two regions here. R1, R2. So if you look at it, you can say that these two regions are space-like separated, right? So first of all, just the language, the region R2, R1, R2 are space-like separated if x1 minus x2 squared is less than 0 for every x1 that belongs to R1, x2 that belongs to R2, right? So that's a reasonable definition. So then the next thing that we want to figure out is, what is the operator equation that encodes the causality equation? Okay? So in this Heisenberg picture language, operator language, what is the condition that I have to see if I know that the physics respect the causality? So that's the condition I want to first get. So what would that be? So for that reason, let's consider a case where I have a operator O, X, operator another 2, this. Suppose let's consider which are not 0. To guide you for now, let's not too much worry about X and Y. If you like, let's just consider the case that I had a sigma X, sigma Y, and that thing, because of technical reason, probably you need to have the 2. Am I correct? Divided by 2, that satisfies SU2 algebra. So I think that's right. You know this, right? Spin algebra or SU2 algebra. So this is the example where you have a 2 operator which doesn't commute. Obviously here there's no sense of like space-like separated, time-like separated. I'm just taking an example. But let me first explain to you what is the physical meaning of having a 2 operator which doesn't commute. Okay, so here's the Gedanken experiment. So there is a room. Okay, there was a room with the lab prepared, and then person, Alice, walked in. And in this room, there's the electron. And Alice performed a sigma X measurement. Okay? It's a classic result. Then after the measurement, obviously, electron will be in the sigma X eigenstate, right? Good. Then, Alice walked out. Okay? And then soon after, now Bob walked in. Oh, what is that? Who is this? Okay? So here, electron is in sigma x eigenstate. Right? So that's that. Bob walked in and he did a sigma y magnetic state. Okay? So then what happens? Now electron must be in sigma y eigenstate. Right? Because sigma x eigenstate can be linear combination of a y eigenstate. So he will pick up one such state, for instance. Now, next day, Alice walked in the lab again. Okay, she is a very diligent graduate student. Okay, I'm gonna do this measurement every day, making sure I'm doing this correctly. And then she's like, who did that? Who did that? Right? There's a criminal in this building. I definitely did the correct measurement. I beautifully set up the sigma x eigenstate. Somebody walked in the lab, did something bad, right? Who is the criminal? So she retracted to the security center. Look at the video. Tell me who did that. So what do you learn from this? A, there's a lesson number one. If you have an operator which doesn't commute, somehow it can affect the result of Alice's original method, right? Something has changed. It affected it, right? Good. B, there's a second important point you have to appreciate here. Every chain of physics happened here. Every chain of physics happened here is within the light column. So Alice first did a measurement. The lab itself, say, didn't move, okay? We don't have a fancy big truck carrying around this thing, so there's a nice. And then Bob walked in, and then Alice got shot. This is a chain. So everything has been within the light column, and that's why two things. Bob used an operator which doesn't commute with an operator that Alice used to do that. That's fact number one. Fact number two, those sequence events were in causal connection. Okay? Then we found out that it can actually affect. Therefore, there's a causal connection. Is that clear? Two things? Okay? So this and that certainly create a causally connected phenomenon. Alright, so that's the setup. Then what do we need to demand? So this is an example that I can experiment, hopefully give you a motivation how to think about the physics. So in order to, therefore, from this exercise, hopefully, causality requires regardless of the context, I don't care where they're coming from, right? But I know that they have to vanish outside of light. Hence, they cannot have any causal influence. Okay, so this is a condition we want to demand from now on. And it is called sometimes okay, so that's the formula, yes.
According to you, then the operator must be the Hermitian operator so that it is the observable.
For now, I'm assuming very good sex. So here, yes, keep going. These are Hermitian operators.
So as I know, as far as I know, the microcausality condition is the condition that is imposed on the field.
Fundamental field, which we will carry out, and I will explain. What if a field itself is not Hermitian operator? How to think about the condition, if that's your question.
So the physical argument only is
for now, yes.
Yeah.
To only the Hermitian operator.
Okay. I was checking my understanding.
Yes, you're right. So for now, because I was discussing in the context, in the language of observation and the measurement, right? I'm implicitly or explicitly, I'm talking about the Hermitian operators. Only the Hermitian operator give you real eigenvalue, therefore we can talk about physical observable. So here, yes, I am having in mind that for any observable operators, meaning Hermitian operators, they have to satisfy that. And then we will now soon start talking about construction of quantum field. Some of them may not be Hermitian operator, yet you will see they will impose conditions like this. You can say why, and I will answer that question. All right, so and this Bob made a good friend afterward, and then finished their PhD last week. Okay, so now I want to construct a really causal scalar operator, scalar fields. Okay, so here we're gonna impose 5 conditions. Some of them are essential, some of them are for convenience, and I'll explain. So number 1, so here let me imagine there's a scalar field. Oh, before that, let me motivation. I want to talk about things like this. You might say, okay, I understand everything. Why do you want to talk about that? So previously, in 2, right? We talked about the particle state constructed in terms of creation operators, right? We talked about occupation number representation of many particle states, right? So everything was in the momentum eigenstate, which was good because I want to manifest that everything respect the translation invariants. Everything was good. However, now, to think about and demand causality, we need an object that knows about the space-time point, right? Only then I know how to talk about the causality, right? Objects which are function of, roughly speaking, function of space and time. So somehow we want to know how to go from, this picture to some object that has a space-time index labeling with it, so that I can impose causality condition and ask what are the properties, what are the properties in the constraint that this has to satisfy. Okay? So that's the motivation. We want to start talking about notion of a field. Okay? Field being a function of a space and time. Okay, so now I want to impose 5 conditions that this phi has to satisfy. So I want to consider potentially several different kind of them. Let me use labeling A, okay? I might talk about several things. So who knows? I might be talking about several different kind of scalar field. So the first condition I want to impose is the causality condition. So here I'm assuming, but again I will answer the question. Here I'm assuming these are I will impose that explicitly. So let me order. Yes. Maybe the other way around may make you happier. I'm going to impose reality condition for now. Okay, but I will tell you this one, sorry. So this is, means I want to look at the real or Hermitian operators, okay? Which has an immediate counter to this discussion. 3, can I cut and move up? If it is iPad, I can. I screw. Okay. Anyway, so let's live with this. And then I need to impose 2 conditions related to Poincaré transformation. So the first, if I take this, if you remember how operator has to transform, if you remember, O has to transform as U dagger U. Okay? Because you start out with a sandwich of transformed dagger, and they just reinterpret in terms of transformation of operator. Okay? So therefore, if I had a P, A, first translation, A, okay, I will need to transform like this, because They're partial by minus sign. I will explain. And then Lorentz. This. Lastly, I want to demand the fact that these operators are linear in alpha and alpha theta. Okay. So let me explain some of them, some of which are not absolutely essential, but let me explain motivation behind this. So let me first explain the number 2, okay? So hopefully now you can read this equation as causality, hermiticity, Poincaré transformation, and boom. Okay, we'll see what that boom means. But let me first talk about the point 2. So in quantum field theory, or in general, we can have a non-Hermitian, there exist non-Hermitian operators, non-Hermitian quantum field. Okay? So for example, we will talk about, I don't know today, there can be a complex field, okay, which is, we can think of it as some of the linear combination of the 2 real or Hermitian operators, right? For instance, there will be a fermion operator, as we talked about, which also is not Hermitian operator. But the point is that every operator can always be decomposed into Hermitian and anti-Hermitian parts, right? And then I can zoom into that part and then work out that way, okay? So that's common number 1. So any operator, which even if it is not Hermitian, I can always decompose that into Hermitian, anti-Hermitian, and then I can play out that way. B, obviously, in quantum field theory, we will eventually construct a Hermitian operators, which is candidate for the observable, okay? And then we can obviously demand the causality condition on that. But as we will develop, once we construct a quantum field, either Hermitian or non-Hermitian, understanding this decomposition, if we impose this causality condition component by component at the level of a quantum field, a quantum field as a fundamental object, as we will discuss, okay? Then, if we construct observables, it will manifestly satisfy causality conditions, even if I start constructing a observable operators made out of that. Okay? So that's the 2 sort of a motivation why, for now, I'm going to just focus on Hermitian operators. Did that?
No, I understand the point that if we impose the causality condition on the fundamental field, then all the observables are, of course.
You might say that's too strong condition.
Yes, that's really too strong.
That's what I was telling you, that there's also notion of decomposition. Also another thing that I haven't say that explicitly was this condition known as a micro-causality. There's a, in a sense, broader notion.
I mean the physical motivation of the micro-causality.
Yeah.
I want to figure out that.
Okay, so the physical motivation of that thing is basically exercise you can follow chapter 2 to 5 of Weinberg. Basically, after the Poincaré transformation properties, then you can understand what is known as a cluster decomposition principle, which is conceptually say that if I have two regions of space and time, which are separated far enough. What do we mean by far enough? And suppose there's a certain dynamical process happening here and there separately, to the extent that the time scale of such dynamics, and then the rate of that dynamics, are in such a way that these are considered to be space-like separated region. Then, probability of combined event has to be factorized into probability of the first event times probability of the second event. This is a cluster decomposition principle. And then one can show that once you demand this cluster decomposition principle at the level of an interacting Hamiltonian cannot have a more than overall momentum conserving delta function. Okay? That's one mathematical piece. And then you can move on later and then put this condition into, okay? And then when you try to now develop a perturbation theory in a sense of Dyson series, one can see that equation like this pops out in a very general ground. And then one learns that this condition has to be imposed on a general ground. Okay, so that's, I mean, I cannot squeeze into that, but that's probably the exercise you want to work.
I figure myself.
Yeah, okay. Good, so that's my quick comment about number 2. That's why I'm just gonna focus myself on this real or permission operator for now, okay? But there's a more general story we can go on. So then let me make a quick comment about this point. Maybe this makes sense, but like exactly why here is minus and here is the inverse, right? That's the single point I want to clarify. So again, we are comparing Schrodinger versus Heisenberg picture. Schrodinger picture is like this, basically. So suppose I had a coordinate with the origin here. Suppose you had a particle like state, the Schrodinger picture, right? There's a particle state, and then this guy actually moved to a point here, A. With the coordinate state fixed, meaning then what that means is that with the coordinate system fixed, you're going to always use a single time independent operator to measure the location of this particle. And then that operator, we always say that this point remains to be origin all the way through, and then it is a state or particle actually moved, and the state particle moved from 0 to A. That's what that part of the description will say. Now you can ask yourself, how can we get the same answer now if I have a particle sitting at a stationary point, doesn't move at all? And you can create the same phenomena. So if you had a first coordinate system like that, but then you want this coordinate system, meaning the operation point actually changes later time. So that you see that the later time saying, you want that the actual operator, instead of saying that this is my origin, you should say that this is my origin. And that observation will say that now particle moved forward. So that's the sense we're talking about here. So I'm talking about operator in the Heisenberg picture sense or passive transformation picture rather than active. And so therefore this actually have to move backward. You see? After that, the origin of this field is equal to x equal to A of original coordinate system, right? So that's why there's an inverse, and this one too, basically rotation sense. Okay, so that's a 3 and 4. What about the 5? So 5, you can go wild, okay? I'm gonna consider this up to alpha to the 500. Okay, good for you. I'm not gonna do that. I want to build up the minimum object at first in such a way that my field, okay, is capable of either producing a single particle excitation or just kill one of those single particle excitation. That's enough, and then I'm just gonna build up using this guy rather than making this just complicated polynomial. I'm just gonna consider that first, and then any nonlinear phenomena that I want to discuss later, I'm just gonna use a composite operator made out of this guy rather than making a horrendous, complicated expression for the field itself. Okay? That's the motivation why this is sufficient to consider linear in alpha and alpha diagram. Good. Now let's launch our analysis. I think we have now precise enough question laid out, and we can launch. Okay, so here we go. So as a first step, let me write down a field at the origin. And then I'm gonna write it as so now, does this equation make sense here? So what I'm saying is this. At a zero origin of the space and time, I'm going to consider arbitrary, a linear combination alpha is there with arbitrary coefficient unspecified as yet. And then at that point, I want to be able to excite particle of any momenta satisfying the on-shell condition. So I'm summing over entire mass shell, right? This is Lorentz invariant mass shell. Is that clear now? Okay, so the only then thing we have to worry about is what are these f and g functions it has to be, right, to be consistent with these conditions. Good? So we're going to first use a Lorentz transformation point first. So Lorentz transformation says that if I do origin, obviously nothing changes. Because I'm looking at a scalar. Okay? So here, let me just write let me write that after, not now. Okay, so let's just impose that. If you do that, this gives you, so this is just a function, and then you get u dagger alpha u. So let me drop the p, and then GOP, u dagger alpha dagger u. Oh. Okay, anyway, it can be slightly the other way around, but anyway, it's okay. So now, you may remember that previously we had an equation like this. You understand there's a u of lambda and then alpha of p. This should be alpha of lambda. Okay, so that's what we determined when we discussed the many particle phenomena. Okay? So that means this is lambda p, or inverse p, or actually, that's probably correct, yes, lambda p. Okay? So now this is Lorentz invariant measure. So therefore, let me make a change of variable. So now I'm gonna just make a change of variable. This is completely unchanged. Now I was just called it alpha of p, alpha of dagger of p, right? So therefore, what I'm gonna get is, again, Lorentz invariant measure, inverse p, alpha of p, alpha dagger of p. And that expression had to be the same as original field, right? That's the condition. So from this, we learned that the coefficient function has to be what? Lorentz invariant function. Correct? Yes? Yes? Therefore, we learned that this function had to be Lorentz invariant. And also for the g. Now, however, we're talking about a single form of eta, right? We're talking about single form of eta. And for single form of eta, the only invariant, Lorentz invariant, one can construct is basically that, which is otherwise known as a constant. Therefore, we learned that this function actually has to be just constant. I mean, it can be mass, but it is just a momentum independent function. Okay? So we can drop the p dependence there and there. Good. Now let's check the translation. This is number 3. So translation says that how can I construct a field in arbitrary x? So from that, I have to rotate backward. IP x minus IP x. So if you do that, you should get the following answer. Again, using how alpha dagger transform in the translation that we talked about last time, it should be f e to the minus I to the x p, 3 e to the plus I to the x alpha dagger. Okay, I'm not writing explicitly, but let me write for once and for all. We are imposing Oisha condition, but I'm not writing it explicitly because whenever you see this, it should be clear, right? This is Lorentz invariant on shell that is imposable. Okay, so maybe it starts appearing like what you have seen, right, in the textbook. But that's not the end, because we haven't determined this yet. Crucially, we haven't seen how this plays a role. So let's see that.
Professor?
Yes.
Is the number 5 comes from some fundamental principle?
Which one? You mean number 5? Good. So my rationale when I was explaining this was that, I want to start out constructing the minimum building block first. Okay? Therefore, I just demanded a linearity because I just want to have something that creates one of them or destroys one of them, not like many number of them. That's fact number 1. Fact number 2, in the context of a scattering amplitude and S matrix, there's a notion that we will discuss what is known as asymptotic state. And if you want to have a quantum field that actually can create asymptotic state, it had to be linear in that particular state. Okay? And then there's a whole, more advanced subjects such as like bound state formation and blah, 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 but that's after, okay? So here it's sufficient to talk about an operator that creates a single propagating loop. But it is not mathematical theorem that all corner field has to be linear in something.
그러면 이미 오퍼레이터를 적어서 저 펀더멘탈 때 컴파지터 만들 수 있다는 건 이기는 거예요.
We can talk about the composite operators. We can talk about like a phi 4 to the x. The composite operator defines a single point.
이미 오퍼레이터.
Arbitrary operator. What does that do for you physically?
그러니까 이게 가장 미니멈 볼 빌딩 블럭이라는 것에 대한
I think has to be, I don't know what exactly you're thinking of. So either zeroth order in alpha p dagger. Right? Zeroth order in alpha p or alpha p dagger. So that basically doesn't do anything about this particle excitation. So that corresponds to the, if you like, vacuum sector of the thing. In the linear order. So that should be responsible for the one particle state Hilbert space. And then higher order. What I'm saying, I'm just gonna construct in terms of phi's rather than constructing higher order in alpha in phi. That was my rationale. Okay, good. So where are we? So we have gone through that. No. This. So let's impose the 2. Condition number 2. So if we impose hermiticity on this, you should get that F star should be equal to G or vice versa. Right? You might say, yeah, I can figure that out. But that has very deep meaning to it. Okay, this is deep. Okay, how deep can it be? Okay, this is deep. So let me say why this can be deep. So this implies the following fact. So therefore, this means, as a one of the meaning, that it's not possible that either f is 0 or g is 0 while still we're getting non-trivial. At the level of corner field, what that means is that you are forced to include both non-trivial piece of alpha, non-trivial piece of alpha dagger. You cannot just do this or that. Okay? Now, that will be crucial now as we understand the causality condition. Okay? So that's that. So therefore, we can now freely take, first of all, let me just normalize. Overall size don't matter, because that just means overall size of the phi. And as we learn more and more along the course, overall size doesn't matter. I can always take the my normalization, so we can just take f to be e to the I, some fate. Okay? Some complex number with the unity. Unity norms, I can just take that. Therefore, if I plug in here, my corner field becomes, I don't know if I need to write that again. So now let's impose causality.
Zeta is a function of P, right?
No, I already told you that Lorentz transformation said that f has to be constant, not any function of P. Okay? Therefore, I'm talking about this stupid number. Okay, the question is there a constraint on this number? Other than the size, the overall size? That's this number. Alright, so now to understand the causality eventually, Now, let's ask the following question. For a given particle species, and then whose quantum state P, can I have a more than one different kind of quantum field that actually can produce that guy, right? So for a given one single particle species with a mass, I'm thinking, and then scalar, am I allowed to introduce two different quantum fields that does the same job? Okay? So for that matter, what I'm gonna do is I'm gonna introduce, so I will write it in the slide notation from now on, okay? Then you understand what I mean. So I'm just gonna write it as F1, and then I'm not writing all integral blah, and then I'm gonna introduce a similar object like this with the different F2. Okay? So suppose let's ask that question. And then let's demand the causality now. So I'm gonna ask phi I of x, j of y, where now obviously I means either one of two, and j means either one of two. Okay? So I want to see whether this can be zero outside of light. And what does that teach us? So to do this, actually I'm gonna introduce a notation. So this piece, I will write it as phi 1 of plus of x. And then the second piece, this piece, what I mean, as operator with the minus postscript. Okay, is that clear? So my notation is including integral. This piece is my phi of minus, and the integral, that piece is phi of plus. Okay? Oh, minus. Yes.
1번에 나와 있는 A, B 인덱싱이랑 오른쪽에 그 아래 첨자로 정시 1, 2번 인덱싱이 다른 걸 나타내는 거예요.
Yes, so okay, probably I didn't have to do this. Previously, I just included this to be general that I can think of several different kind of species of particles. Okay? Like you say different particles. Probably I introduce different field. Here, subscript 1 and 2 means that for a given single species of particle, I'm asking whether it is sensible to introduce multiple different quantum fields that achieve stuff. And if I demand the causality, what do we learn about that? So in a sense, you just forget about this forever. Okay? So sorry if they just raised the confusion. Okay, so let's proceed this exercise. And let me say historically really quickly why people even invented this plus minus thing. So historically, I think it's Heisenberg and Pauli. When they look at this phase, which starting having a e to the minus I et, and that corresponds to a correct time evolution phase that you see from a quantum state evolution. Okay? So they thought, okay, this corresponds to positive energy mode. They put the plus sign there, but likewise, if you look at this, you start out with the plus I et, which is minus I minus et, so that looks like negative energy or negative frequency mode. Okay? So that's historically why this notation probably was invented. However, forget that. Okay? We are not dealing with a quantum state evolution. We're talking about quantum operators here. Okay? And so what means positive and negative? We should be strictly in terms of operator language, not in terms of state language. So this will only confuse you. However, I'm just gonna use the notation just to divide it into two pieces. Okay? Is that clear? Okay, so if we do this, what should you get? So at least let me set up the computation. J plus okay, so remember this thing had an alpha, this thing has alpha dagger, this thing had alpha, this thing had alpha dagger, right? And the computation relation of alpha with alpha vanishes, alpha dagger with alpha dagger vanishes. Right? And these are creation knowledge number. Only the alpha with alpha dagger is non-trivial, and the vice versa, right? So the only non-trivial contribution to this calculation, therefore, comes from this. This. Okay? Okay, so what is this? What is this object? If you explicitly compute it, it's quick to do it. I'm very sorry. Well, not a lot, but a little bit. So F1 star. So I'm just gonna take out only the space part okay? I don't want to, dangle around that. So is that clear? I'm only calling the 5 plus minus to be this piece without a overall constant this. So that means that I have to put it in what? Fi, Fj star. Am I correct? Good. Let's see if I can do this. Am I failing already? No. Huh? It should be J I star. Okay? Good. So now, what is this object? You can compute this. Basically, you have a product of this. Okay, let's just show this. This is important. That is important, but let me introduce a notation. Triangle plus, self-square plus, x minus y. And I'm just gonna give mass information, which will be important. Now I'm gonna define that function as this, but let's see how that looks like. A claim is that if you do the computation, you should get the following answer. I mean, this is a straightforward single delta function calculation, so I'm not gonna bother. Okay, it is that object. Because I want to hit the punchline at this. Let me move on. Okay. So what we need, therefore, is I want this to be 0, right? I want this to be 0. Now, what is this object? So this is equal to, this is a minus of the other one, right? And so you see that this is minus y minus x, crucially, m squared, right? X minus y, okay? So what we learned is that that commutator that captures causality is given by Fi, Fj star minus y. Okay, good. So now we need one piece of extra information to simplify this, which is the following. So consider a vector, 4 vector, and then we can consider 2 different kinds. So one is a positive, so this is time-like, as we talked about. So just to give a numbering, so let me just call k squared, which is positive, which is time-like, which is x0 squared minus xi squared. And this shows that x0 squared should be equal or greater than k squared, right? So let me just start drawing in. So in this t and x, and then we have seen several times. So this time-like case corresponds to x0 component, minimum value being square root of k, but greater than or equal to. So there is one positive branch, one negative branch. We talked about this. Yes? And no proper orthogonal transformation can flip one to the other. So they stay in here, right? And then transformation can move along this direction. What about the space-like? So that's the first kind. what I want the space like, once again, this is x0 squared, xi squared. Then we call that to be k squared, which is now negative. Probably I call minus that to make sure. In this case, you should convince yourself that ki is bounded from square root of ki, but greater than or equal to. So that gives you the following hyperboloid. Now xi, the special component is bounded like this. And then that's what orthochronous, proper orthochronous Lorentz transformation can move around. Okay? So this is now then to be this. So the point is that for space-like separated, for instance, if I pick this point, I can always do a Lorentz transformation. For instance, can flip x2 all the way to minus x and so on. That is possible by proper orthochronous transformation. But also, you can always bring this into this point as an equal time slice. So for any two points which are space-like separated, we can always do Lorentz transformation put on an equal time slice. And then we can impose, as you will see again and again and again, equal time commutation relations. Okay? So that's why this notion of equal time commutation relation comes in. That we want to bring in the notion of causality, which are always about the space-like separated, so that you can always do that by this feature. Okay? Good. So going back to this, now if I look at the space-like separated x and y, I just show you that if you had any function of x, you can always do the Lorentz transformation such that it is equal to f of minus x. You can go from here to there. So that means that this, on space-like separated point, is equal to x minus y m squared. Okay? Therefore, this entire expression collapses to fi fj star minus fj fi star. This. Now, one last thing I want to say is that one of the exercises we did when we talked about this causality check, actually that thing was given by x. Okay? Yes.
Delta is just the integral.
Oh, you mean this?
Yeah, delta.
This is basically that.
Okay.
So in chapter 1, although I never said chapter, in 1, when we were exercising this, the integral we had to do was this, okay? Without 1 over 2e basically. Everything is same except the 1 over 2e. And we found out that this is non-zero outside of Lycon, okay? And this and that relation is that if you take the derivative of this object with respect to zeroth component, you bring down the energy component. You cancel out this e. Okay? And there's an overall factor which is minus I over 2. So these and that are related by type derivative up to a factor of I over 2. You see what I'm saying? And that was non-zero. Derivative was non-zero. You can argue, you can show that this is also non-zero outside of Lycon. Okay? So this is non-zero outside of Lycon, so causality can be fulfilled only if this is 0. And hopefully you see that then, it is possible only if there's only one f, this is the same, and then this is some phase. So given one species of particle, you cannot talk about multiple random quantum fields. Because that, there should be one, otherwise you will have a random causality violation. One particle, one quantum field. And then that can be satisfied, but this thing now you see this as the uniqueness of the field itself. But later, next time, I will discuss this minus I as a true deep meaning, okay? So let me just spoil you. That just means that there's a quantum field piece which has a particle piece, as I will talk about next time, and the anti-particle piece. And then space-like separated propagation is a particle contribution, and the anti-particle contribution is precisely cancelled to restore causality. And that's why I mentioned last time that we need to talk about many particle physics, at least the notion of antiparticle. Otherwise, you will never get to causality. Okay? So, therefore, overall, finish up the lecture. Now, I can basically talk about just where you had an iterative data. I can rescale this together for my mu alpha. The your quantum field will just be integral into the minus IP dot x alpha and the Higgs permutation conjugate, because I can just scale up this thing. Okay? And you can convince yourself that just observing phase will not change commutation relations of this, or normalization, whatever. Okay? Because you always get alpha dagger commutation relation. They cancel out. Good. So that's the end of today's lecture. We have to walk out this room in a minute. If you have any question, I'm happy to address that.
호라, 마셔. 그거 마감.